Hi guys, it's Nicole Mashburn again. There's really not a PowerPoint for this lecture. As you're watching this integrity, there is a little printer icon if you want to print off what I write. But I just want to take just a few minutes and kind of tie up some loose ends or put some things together for you when it comes to action potentials, membrane potentials, and there we go. Action potentials, membrane potentials, what's going on at the neuromuscular junction, and contraction. You need to be able to watch those A&P flicks that are in your shell and the videos associated with the lecture videos associated with that. And then you need to step back and take a piece of paper and just think about this as one long continuous chain of events, okay? And you need to be able to basically write these steps down. And what I mean by that is you need to be able to just take a piece of paper and go, okay, I got to charge my battery. What does that mean? Got to get that axon of the neuron ready to go. So think about what's going on there. So in your axon, you've got those sodium and potassium channels, right? They're leak channels. You have sodium is a little higher on the outside, potassium is higher on the inside, right? You've got potassium leak channels. You've got sodium leak channels. You have more potassium channels than you do sodium leak channels. Potassium's leaving, sodium's coming in. That's leaving you that net negative on the inside, which sets up your battery. Makes the inside negative, the outside positive. Okay? What is key to keeping that battery charged? Because if you just let nature take its course, eventually that would just reach equilibrium. Something's got to be happening to keep that battery in place. And that's the sodium-potassium pump, which requires ATP to pump potassium against its gradient and sodium out against its gradient. So you set up your battery, you've established your resting membrane potential. Now you've got to generate an action potential. Remember? So here's our axon, here's our neuron, and what we want to do is we want to get a signal. Here's our muscle. Okay? So we want to get a signal, an action potential, from the neuron down to the end of the axon, and somehow we've got to get an action potential over here. So we need to be thinking through what's got to happen to do that. How are we going to get this stimulus, this action potential, from the neuron over to the muscle? So we generate our action potential, and it carries down the axon. What does that mean? Remember, draw your action potential. You have a stimulus, which is a voltage, an electrical stimulus, which is causing voltage-gated sodium channels to open. So sodium is going to come in, and you're going to have more positives coming into the cell. That's going to cause your membrane potential to rise. That's called depolarization. Once you reach about positive 30, those sodium channels are going to close, and the voltage-gated potassium channels are going to open. Potassium is going to start to rush out, taking those positives with it, bringing this membrane potential back down to negative. It's going to overshoot a little bit, called hyperpolarization, and then reset to normal using the pump. Okay? So this is just going to go down the axon until it reaches the end. Now, that action potential doesn't just jump over to the muscle. Okay? It's got to be turned into a chemical event. So this is an electrical event. You need a chemical event to restart the action potential on the other side. So let's go to another slide. Let's blow up our synapse. Hang on. Can't get my, hang on. So let's get our synapse. And what's the synapse? That's where the axon terminal and the muscle come together, right? That's our synapse. So now we got to think, what do we do? What are we doing here? What's going on? Well, the first thing, the action potential's got to come down to the end of the axon terminal. That causes voltage-gated calcium channels to open. Calcium rushes in. Okay? Now what happens? That causes the neurotransmitter, which in this case is acetylcholine, to be released into the synapse. The acetylcholine is going to diffuse across the membrane. It's going to do what? Bind to its receptor. That receptor is a ligand-gated channel. Alright, so once this acetylcholine binds the receptor, that causes that to open, you start to get that movement of sodium and potassium again, and an action potential is generated. So you have electrical event again. So you've taken an electrical event over here, converted it to a chemical event at the synapse, and then regenerated your action potential along the muscle cell. Has your muscle contracted yet? No, we're still getting there. But I'm just saying, you've got to be able to walk through this step by step by step. Alright, so let's blow up our muscle. Here's our sarcolemma, which is the cell muscle membrane, right? Here comes your action potential. It's traveling down the sarcolemma. Well, it's got to go deep into the muscle, right, so that all the cells of the muscle, so you can stimulate the cells as all at the same time, so you have a nice fluid contraction. So the action potential is going to go into the cell, or into the muscle, using those T tubules, or transverse tubules. Once it gets inside the T tubules, it's going to meet the triad, which is where the sarcoplasmic reticulum and the T tubules come together, and that's going to cause what? Voltage-gated, or basically voltage-sensitive calcium channels to open and release calcium into the cytoplasm. So now we have calcium in the cytoplasm. Has the muscle contracted? No, not yet. What do we got to do now? You've got to set up your sarcomere. Okay, so you've got calcium out here. Calcium has to bind troponin, right? So calcium's going to bind the troponin, and that's going to cause the troponin to change shape and move off the tropomyosin. And that's going to what? Free up the myosin binding site on actin. So now you can have cross-bridge formation. So here's my myosin, here's my actin, and now that the troponin and tropomyosin have moved, you can bind your actin and your myosin. So now you got to go through your cross-bridge cycling. So what does that mean? That's when actin and myosin join. And what do you have to have for that to happen? ATP. So you have to have ATP to cock the myosin head, then the myosin is going to bind to the actin. You're going to throw off part of that ATP. You're going to get the power stroke. Oops, sorry. ATP is going to come back in, cause the actin and myosin to dissociate, and just start the process over and over again. So you need to go through cross-bridge cycling. Now the muscle is contracting. And this is going to go on as long as you still have a stimulus coming down from the neuron. So as long as there's an action potential coming down there, and calcium's coming in, and acetylcholine is being released and binding to the muscle, you're going to get contraction. So in order to have relaxation, you've got to stop the stimulus. You stop the stimulus, you'll stop the inflow of calcium, you'll stop the release of acetylcholine. Acetylcholine will no longer bind to the ligand-gated receptor, and you won't get the action potential going down the muscle. Now, as long as there's acetylcholine in the synapse, it will continue to bind to that receptor. So you've got to get rid of it, and there's two ways. You can either let it float away or diffuse away, or you can break it down with an enzyme. And we call that acetylcholine esterase, and I'll just abbreviate it ACHase. So acetylcholine esterase comes in, breaks down the acetylcholine, so you don't get that binding anymore. Now that there's no action potential traveling down the muscle, there's no release of calcium into the sarcoplasm, right? So there's no need for troponin to be bound anymore. Without this stimulus, without this calcium being released anymore, the calcium pump is now going to be turned on. It's going to pump the calcium back out of the cytoplasm, releasing the troponin. The tropomyosin will roll back over the myosin binding sites on actin, and the muscle will begin to relax. So that's kind of the steps going forward into contraction, and then the reverse steps that have to occur in order for a muscle to relax. And I did that in about 4 minutes. It didn't take me very long at all to go through all those steps. And that's really what you need to be able to do, is think about what's going on from the very beginning, get your battery set up, go through the steps of action potential, the steps at the neuromuscular junction, what happens at the end of the axon terminal, what happens to acetylcholine, where does it bind, how does an action potential start on the other side, how do you get calcium to be released, how does it bind troponin, what goes on the cross-bridge cycling, and then how does muscle relax. And just kind of keep watching those A&P flicks until you can follow along with that. One more thing I want to talk about is, and this kind of carries us into unit 4, the nervous system unit, is when you're looking at the axon, at the synapse, the axon terminal, and the muscles. So this is your pre-synapse, and this is your post-synapse. We're going to start talking about some drug interactions later on when we talk about the nervous system. And some drugs work at the presynaptic side, and some work at the postsynaptic side. And so I kind of want you to start thinking about that. If you wanted to keep somebody relaxed, what are some options that you could do? How could you make somebody not be able to contract? Well, you could maybe block those voltage-gated calcium channels here. If calcium can't come in, then acetylcholine can't be released, right? If acetylcholine can't be released, you won't get a contraction. So you could do something at the presynaptic side, or you could maybe have some kind of a blocker, a receptor blocker. This ligand-gated channel is just a receptor for acetylcholine. You could put something that looks a lot like acetylcholine that will actually bind there and block it so that acetylcholine can't bind, and nothing will happen. No action potential will be generated. And so as we think about these drugs, we move on into the nervous system, I want you to think about how they could work on this end or that end. And there may be a question on your exam, on the muscle exam, thinking about what you might could do to cause someone to not be able to contract. So be thinking about that. A little bit of critical thinking going on. All right, that's all I wanted to say. Just kind of wanted to pull the things together for you and make sure that you do focus on this. This is probably the hardest physiology that you'll encounter this semester. There's a lot of steps, but you need to get a good handle on it, because understanding this is key to understanding the nervous system. And later on, it'll also come back and you'll start to see some similarities between this and how the endocrine system works as well. You have hormones which are basically kind of like acetylcholine that have to bind receptors, and things have to happen. So hopefully this will start to introduce you to those concepts. If you have any questions, email me, call me. Feel free to ask me or any of the instructors at Calhoun, and we'll be glad to help you.